Hello, everyone. My name is Omar. I am from the University of Illinois at Urbana-Champaign. The work I'm going to be presenting on today is the punching shear capacity of plate dowel joints for slabs-on-grade. You know, when we talk about dowels, rarely do people talk about punching shear capacities. You don't assume that there will be any punching, but with tapered plate dowels, we believe that there's a reason to talk about punching as a critical stress. My advisor, Jeff Raisler, as well, helped me with these slides in this paper. So at the beginning, I'm going to talk briefly about dowels, introduce them to those who may not be familiar with them and how they work and what they do. Then I'm going to talk about tapered plate dowels, which many people, even who know dowels, are not familiar with. Then I'm going to talk about the experimental investigation that we ran and the results of these experiments, and then the model that we took and copied and used for punching shear analysis of tapered plate dowels. First, I would like to acknowledge that this research was funded by ITW, Illinois Toolworks, Commercial Construction North America, CCNA, and that all the tests were done in their laboratory in Lake Forest, Illinois. Dowels. So what are dowels used for? Dowels are used for transferring the loads across joints for jointed slabs. So two adjacent slabs, if you do not have any aggregate interlock that's holding them together or that's transferring some of the load at the edges, dowels are basically helping us reduce the edge loads on these slabs. And in turn, this limits the differential deflection between slabs, which, when rolling lift trucks or trucks in general are passing across these joints, they may chip, they may spall these joints if you do not have a good if you do not limit the differential deflections. And so what are the usual dowels conventional dowels that are used in all pavement applications? Usually they are 18 inches long. They are 0.75 to 1.5 inches in diameter. They're epoxy coated and they have a smooth surface. Why? Because you do not want them to restrain these joints. You want to make sure that they are, when concrete shrinks and expands, that these dowels are allowed to slide through the slits of these joints, of these dowels. So why do we use dowels again? Well, assume that you have a 15-inch concrete airfield slab and that you have a 300-ton A350 passing across these joints. At the edge of this slab, according to Westergaard, the stresses that will be accumulated for one wheel of this gear is around 770 psis. This is assuming that you have zero load transfer efficiency. Now, if you increase the load transfer efficiency to 75%, the load at the edge reduces from 770 to around 480 psis. Now, what's contributing to the 75% LTE is not necessarily the dowel, yes, but largely it will be maintained because of the dowel. So what are the problems that people face when working with dowels? Engineers, practitioners, is corrosion, one of them. So they decided to just epoxy coat it with this green coating. I'm not sure if you can see that it's green, but they epoxy coated to reduce corrosion, but also to sort of increase the sliding, the smoothness of the surface. Loss of effectiveness stemming from looseness, fatigue, cyclical loading. The concrete at the top and the bottom of these dowels is exposed to the small bearing stresses that are slowly chipping out of the cement. And then finally, if you have a conventional dowel, a prismatic dowel, a dowel that looks like a beam, if you do not align these dowels properly, there is a risk of cracking. This cracking comes because concrete is shrinking and expanding at several times. At an early age, concrete shrinks because of the moisture shrinkage, and then cyclically because of, over seasons because of thermal shrinkage. And finally, I just want to point out that dowels, when we design them, we're not talking about a single dowel across the joint. We talk about a group of dowels, and there's a mechanism to calculate, how the wheel load is transferred into the other side, and how even this transferred load is then, distributed among the adjacent dowels into one dowel. So the critical load is the one that we're sort of going to be talking about from now on. What are tapered plate dowels? So there are two types of dowels generally. One of them is the the usual dowels we know about, the bar dowels. Usually people use round dowels, and then square dowels have also been used in some applications, external applications. But then there are also plate dowels. Plate dowels are usually used for commercial industrial flooring systems and adjacent external flooring systems outside of these facilities. And these include rectangular dowels, and they include as well, the diamond dowels. And not all these dowels are used for all the same applications, but yes, this is what a tapered dowel looks like. It's a dowel that basically is not prismatic in shape. It is a plate dowel. It's not a round dowel. It's not a bar dowel, and it has a changing cross section across its length, whether it's changing in one direction or it's changing about its midpoint in both directions. So what are the advantages of tapered plate dowels? One of them is that it has a larger load-bearing area. So you reduce the amount of stress that's being applied on the concrete cyclically, and you reduce the losing of this material, of the cement, and slowly chipping off the cement around the slot of the dowel. Two, according to ACI 360, you can actually place tapered dowel closer to the intersection of the joint. You do not have to place it at 12 inches at least away from the corner. You can place it at 6 inches away from the corner or from the sort of intersection of the joints. The reason for that is because, the amount of shrinkage that's happening at these intersections is higher than what you would see around the edges, the rest of the edges. Three, and most importantly, and the one I kind of alluded to at the beginning, it allows for the free movements of the slabs. It almost eliminates the restraint that you would see at the corners, at the edge, at the edges from misaligned dowels. Now, how common is this misalignment problem? Like, is it really that significant of a problem? Well, NCHRP reports 637. It looked into 60 different project sites. And they found that, on average, the longitudinal misalignment of dowels is at approximately 0.86 inches. And that 17% of dowels had a misalignment of approximately 1.5 to 2 inches. Whereas the horizontal skew or vertical tilt, both of them, almost 30% of dowels had a tilt of approximately 0.25 to 0.5 inches. And 10% had more than 0.5 inches skew or tilt. So misalignment is a problem that you see often in the field. So what are the critical dowel responses that we usually look at when designing these dowels? Conventionally, from Freeburg, these were kind of allocated. These were chosen in the 1940s. And they are differential deflection, bearing stresses, dowel flexural shear, dowel flexural stresses, and dowel shear stresses. There are methods to calculate them. I'm not going to go into the details this time around. But the fifth one, which we're considering in this study at least, is the punching shear of the concrete. Now, we know, at least from the numbers that we will share hopefully in future publications, that plate dowels perform better in terms of bearing stresses. But also we know that round dowels perform better when it comes to punching shear. For a round dowel that has almost the same amount of steel that a tapered dowel has, a tapered plate dowel might fail at 7,000 psi's loads, but a round dowel would fail at around 10,000 psi's in punching shear. So yes, there are huge benefits for tapered plate dowels, but with it we have to consider other critical responses. So our experimental analysis and basically what we did in our experiments is we had three different tapered plate dowels types. We had a diamond dowel, we had a trapezoidal dowel, and we had a hexagonal shaped tapered plate dowel. All these dowels were at approximately 12 inches in length. They were approximately 0.5 inches thick and almost 3 inches wide. Of course, they vary, the geometries vary, but generally this is what they had. This is what they looked like. And then we took these dowels and we centered them at the joint so that we had only one side of these dowels embedded in concrete. And then we loaded them by pulling them upwards immediately at the location adjacent to the slab face. But we did that not only at 0 inches offset, we also did that at 1 inches offset, and we did that at 2 inches offset. Why? To represent the misalignment that we talked about, discussed in a couple of slides ago. So what we did is we applied, we applied cyclic loads, 5,000 cycles approximately, maximum load 2,000, minimum load 200. And this was the experimental setup at the ITW laboratory. So you have here the dowel. You have almost 7 LVDTs placed on top of the dowel, almost in a line, and it's placed in a big slab. It's a large-scale experiment, and we repeated for each dowel type almost 3 times for each dowel type, and offset 3 experiments. And we loaded them then after the cyclic loading into a static load until failure. As you can see, this here shows the LVDT responses until failure. And this is what the failure looks like. And they all had the same shape of failure. And it looked like a punching failure of concrete. And these are the results. What we found is that, generally speaking, these orange bars represent the punching shear capacities of the trapezoidal dowels, the single tapered dowels. And in every offset case, so this is a 0 offset, 1 offset, 2 inches offset. In every offset case, we had the trapezoid dowel perform better. And then we had the hexagonal dowel, and then we had the elongated diamond dowel. In order, this was, in general, their performance at every offset level. But in addition, there was the advantage for the single tapered dowel, that it had a narrow end, and it also had a wider end. So the wider end of the dowel, even at 2 inches offset, had a higher punching shear capacity than the 0-inch narrow end trapezoid dowel. Now, why are these dowels not performing almost similarly or very similarly? Well, one of the main reasons is the area. Definitely. So the trapezoid dowel had almost a 28-inch squared surface area, whereas the hexagonal dowel had almost a 21-inch squared surface area, and the elongated diamond dowel had almost an 18-inch squared surface area. This figure that I posted on top of the punching shear capacity figure, it shows only the embedded dowel area. Embedded area of the dowel in the concrete. So you see here that the embedded area of the dowel at 2 inches offset in the wide end of the trapezoid had even more, it was even larger than the 0-inch offset case. Or, sorry, it's almost the same. It's a bit smaller. So there's some kind of a correlation between the amount of steel embedded in the concrete and the punching shear capacity of these dowels. Now, let's assume that you have a forklift, a 5-ton forklift, single dowel load. The critical load on a single dowel, you can actually find it to be at approximately 3,000 pounds. 3,000 pounds for many of these dowels is not far from the capacities that we're finding. And this is not, we're not even talking about, say, we want to apply these dowels in roadways and pavements, external pavements and highways. So finally, just briefly, because I'm running out of time, what we decided to do to predict these dowels is we went to the PCI handbooks, equations for concrete breakout from anchors that are embedded in the concrete from the precast and pre-stressed concrete pavements. And this is what the original equation looks like. It's, it looks complicated, but it's a few factors and coefficients that are combined together, and they give you a good prediction for anchor failures. And in theory, and one of these factors or coefficients is the projected surface area coefficient. If you see, this is an image from the PCI handbook that shows you the projected area for these anchor group of anchored. The anchors. And I just wanted to, emphasize how similar the failure we saw between the tapered plate dowels and these anchor groups looks like. So finally, this is the simplified equation of our kind of adoption of this original PCI handbook equation. And after using this equation to predict the punching shear capacity of these dowel types, we found that, in general, we got good results. We also got experimental data from ITW from 2017, so we ended up actually testing 81 groups of dowels, 81 dowels into this analysis, into this, validation of this model. And Highlighted in here in green are anything that was predicted in less than 10%, anything more than 10% to 20% in yellow, and in anything more than 20%, sorry, this is an error. Anything more than 20% error was in red. On average, the error that we had was at about 4%. And yes, under-predicted dowels were, we had almost 4 or 5 under-predicted dowels that were more than 5% off, out of groups, sorry, out of this like set of almost 20 groups of dowels. And I just wanted to highlight, do we have 15 or 17 minutes? Okay, so again, remember when I gave the example of the forklift with 3,000 pounds? Look at this case, where we have a concrete that's only 2,000, that has only a compressive strength of 2,000 pounds, and that has a, it is a PD3, it is a trapezoidal dowel, and it's embedded in, it's in a 6-inch thick concrete pavement. You find that its predicted stress, actually the actual stress, the punching shear stress that they got from the experiment was at around 3,300 pounds only. Why would you have a concrete that's only 2,000 pounds? Well, it might be just 14 days old. It might be only 7 days old. It might have had a slow hydration process. So if you're loading these slabs early on, what kind you might end up with a failure, a punching failure for these dowels if we do not account for the punching capacity as a critical response. And I can talk about other examples, but in general, my conclusions, my findings were, our findings were, you know, offset tapered plate dowel joints significantly reduce the punching shear capacity of these dowels. To the punching shear of TPDs is sensitive to concrete strength, it's sensitive to the embedded length and the effective width and the concrete cover. All these factors, we got them from the equations, from the equation that we showed. The trapezoid dowels showed highest punching shears out of the different types that we had. But remember that the trapezoid dowel also had the highest area and amount of steel. Then also single tapered dowel, or basically the trapezoid dowel, they retain higher punching shears in one end than in the other, the wider end. This is one of the advantages of having just a single taper design. And finally, the equation we got from the PCI handbook for precast and pre-stressed anchors was we were able to use it to predict and estimate the punching shear capacities of these dowel types. Thank you very much, and you know, if you have any questions, I'd be happy to answer or hear your contributions.